In this video, we're finally going to take a look carefully and formally at Taylor series and their closely related cousins Maclaurin series, which is going to basically just be a special case of Taylor series. In the last couple of sections, we've been building towards the idea that we can represent a function using a power series. So if we start off with that assumption, we've seen that we were able to represent a couple of specific functions like 1 over 1 minus x, the natural log of 1 minus x, things like that. If we assume that in general we can represent functions using some power series, we just need to figure out what that power series looks like. So if we assume that our f of x can be written as a power series, so that would mean our f of x would look like some c0 plus c1 times x minus a plus c2 times x minus a squared plus ... and that this is valid over some region, basically where we have a radius of convergence r, and so that this representation is valid over some region defined right here, then all we need to do is determine what these coefficients c's are, right? X minus a squared, and so on. We have those values. We'll know ahead of time what value of a we're picking, where we're centering this function. X is the variable that we're using, that we're defining the function based on anyways, so we really just need to determine the c's. So if this is true, then all we need is to determine the coefficients c. So c sub n. So let's actually take a look and see if we can figure out some of these. The first one, c0, is actually pretty easy. So let's actually find these. Let's start with this. Let's find them. So the first one I want to start off with is c0, the first coefficient sitting right here. If I look at the way that we've represented this function, if I plug in x equals a, this term will disappear because it's x minus a, so this will be 0. This term, x minus a squared, will disappear. It will be 0. And every subsequent term will disappear. They will all be 0. The only term that will survive is this first term that isn't multiplying any factors of x minus a. So basically what we're going to do is plug in x equals a. And when we do that, what we will get is, on the left, f of a is equal to c0 plus a whole bunch of zeros. c1 times a minus a, which is 0, plus c2 times a minus a squared, which is 0, plus ... a whole bunch of other zeros. And so we wind up getting out of this is that f of a is equal to c0. So f of a equals c0. Note that I'm going to leave a little bit of space here. In fact, let me make it extra explicit. We're going to come back and modify this in just a little bit, but for now, it's just c0 with a factor of 1 here. But we're going to look for a pattern overall as we develop approaches to find these subsequent terms, so c0, c1, c2, and so on. So let's see if we can figure out how to find c1. So let me just put the word find here. Find c0. Now I want to find c1. c0 was particularly easy because it involved basically plugging in x equals a and killing off every term but 1. If we could do the same thing here, figure out a way to plug in some value into a representation that would kill off every single term except for this term right here, that would be wonderful, right? This is the one that involves C1. Is it possible to find a way to kill off every single other term in this series? And the answer is, if we're a little bit clever, yes. What we're going to do is, instead of just directly plugging in x equals a, I'm going to differentiate both sides of this function. So I'm going to take the derivative of the whole thing. And when I take the derivative of this term right here, that's the linear term, the x dependence will disappear and it'll become a constant when we take the derivative. And all of these other terms that fall after it will still have a dependence on x. They will all still disappear when we plug in x equals a. So what we're going to do in this case is differentiate. And then plug in x equals a. So on the left, differentiation is easy enough. The presumption is that we know this f of x that we're trying to represent, and so we should be able to differentiate it. So I'll have f prime of x, and again we're going to evaluate that at x equals a in just a little bit, but that should be equal to, when I take the derivative of the original function here, the derivative of the c0 is 0, it's a constant. The derivative of this term will just be c1. You can think of it as c1x minus c1 times a, which is just a constant. So that first derivative, the first term that shows up in our first derivative, is simply going to be c1 times x. Or sorry, it's going to simply be c1, because we take the derivative with respect to x, and the derivative of this portion just becomes 1. The next term, when we take the derivative of the term that involves x minus a squared, again, the c2 is just sitting out in front. It's a constant. And I just need to take the derivative of x minus a squared. And by chain rule, I'll have a factor of 2 that gets pulled down, and then we take the derivative of what's inside, which in this case is just 1. So I'm going to get c2 times 2 x minus a. And I'll add in the next term. Hypothetically, I didn't write it up here, but the next term we would have is c3 times x minus a cubed. What would its derivative look like? Well, it would be c3 times 3x minus a squared plus ... So this is what that next derivative of the next term that wasn't written up here would look like. And now we're going to plug in x equals a, and I'll get on the left f prime of a is equal to c1 plus c2 times 2 times a minus a, which is 0, plus c3 times 3 times x minus, sorry, not x, a minus a squared, which is 0, plus ... All the subsequent terms will be 0. And we get that f prime of a is our value for c1. So we have a representation up here for what c0 looks like. Now we have a representation for what c1 looks like in terms of the original function f. And we can continue in this manner. So let's find c2. To find c2, hopefully you're starting to sense a pattern here. We differentiated the original function in order to make c1 term be the only surviving constant. If instead I take the second derivative, these first two terms will disappear, and it'll be c2 that is a surviving constant. So I'm going to differentiate the derivative that we just found. So essentially differentiate again and plug in x equals a. So f double prime of x, the second derivative, we can find by simply taking the derivative of the first derivative representation that we've got right here. So when I take the derivative of c1, which is a constant, that'll just be a 0. I'm not even going to bother to write that one down. when I take the derivative of this term here that involves c2, I'm not just going to get c2 by itself. The derivative of the x minus a term is going to be 1, but I also have this extra factor of 2 sitting here. So I'm going to get 2c2 when I take the derivative of this term. When I take the derivative of this term, I'll have c3. I'll have this 3 here. This power of 2 will come down, and I'll have the x minus a. So I will have plus, in this case, we'll have c3 times a 3 times a 2 times our x minus a. And then if I think about what the next term after this one would have looked like, so it would have been the derivative of the x minus a to the 4th power term. The next term here would wind up looking like, if we follow the pattern, it should be c4 times 4x minus a cubed. So what would its derivative look like down here? So the next term, what I'm suggesting is it's going to be c4 times this 4 that we've got here, times taking the derivative of x minus a cubed will bring down another factor of 3 times x minus a squared plus ... So this is what the second derivative of the original function looks like. The first derivative gave us the factors of the 2 and the 3 and the 4 and so on, and the second derivative allowed us to pick up another factor of 2 here, a factor of 3 here, and so on as we take repeated derivatives. If we plug in x equals a, then f double prime of a is going to be 2c2 plus c3 times 2 times a minus a, which is 0, plus c4 times 3 times a minus a squared, which is 0, plus ... a whole bunch of other zeros. And this gives us a representation now that we can solve for c2. If I just divide both sides by 2 here, then we will be able to get c2. So if we solve for c2, I have, in this case, that f double prime of a divided by 2 is equal to c2. And I now have a representation for what the coefficient c2 looks like. Let's do one more of these so we can start to see the pattern more clearly. So let's say I want to find c3. All we need to do is differentiate yet again. And plug in x equals a. So in this case, because we're differentiating again, we'll be up to the third derivative of x. And that third derivative will look like the derivative of the second derivative. So this first term is just a constant. The derivative of that constant will be 0. Again, I'm not even going to bother to write it. So this is the next derivative that I need to look at. I'm going to have c3 times 2, that constant, times the derivative x minus a, which is simply 1. So this one is going to be, I'll have 3 times 2 times c3. That is the derivative of this term. What is the derivative of the next term? So the next derivative is going to be plus, I'll have, let's see, we've got c4 times 3. Those constants will all survive the derivative. And now I'm taking the derivative of x minus a squared. That will be 2 times x minus a. So I'm going to get times 2x minus a. And so on and so forth. And since we're kind of stopping here, we don't really need to go much further than this. But I guess, again, hypothetically, what would the next term have been? The next term would have been an x minus a cubed, but after the second derivative, that one would have started off as an x minus a to the 5th, so it would be c5 times 4, and we'd pick up an extra factor of 3 here. So long story short, I'm not going to worry about that term, but when we plug in x equals a, I'm going to get, in this case, again, I'll just leave it as 3 times 2 times c3, plus C4 times 4 times 3 times 2 times a minus a, which is 0, plus a whole bunch of other terms that are all also going to be zeros. And what I wind up with in this case is that if we solve for C3, it's going to be f triple prime of a divided by 3 times 2. And that's what's equal to C3. And I'm intentionally not rewriting this 3 times 2 as a 6 because I want to start to recognize a pattern. I have 3 times 2 here. You can see the next time we'll be solving for C4, it has a 4 times 3 times 2. The one after that will be a 5 times 4 times 3 times 2 that we didn't write. And if we want to make it totally clear, we could have even thought about these other ones as involving essentially a factor of 1 sitting in front of all of these. So I could write this as 3 times 2 times 1. I could write this as 2 times 1, and so on and so forth. So looking at this, my hope is to recognize that what we've really got sitting right down here in the denominator of each of these terms is really, this is 3 times 2 times 1, which is 3 factorial. Similarly over here, this one is 2 times 1, which is a 2 factorial. Over here, there was nothing in the denominator. You could think of the denominator as being a 1, but what's 1 if not 1 factorial? And even here, again, we have a denominator of 1 here. It turns out that that is how we defined 0 factorial. 0 factorial equals 1. So keep that in mind as we do all of these. We can keep this pattern going. We have defined 0 factorial to be 1. That is the convention that has been adopted. So just keep that in mind. So let me just write that here to make it clear. Adopted by convention. Okay. So if you start to recognize the pattern, what we see is the following. So if we follow this pattern, if I want to find Cn, the nth coefficient, it's going to be, so for example, to find the third coefficient, I had to take the third derivative of f and then divide by 3 factorial. To find the second term, C2, I had to take the second derivative and divide by 2 factorial. To find what we were calling the first term, I had to find the first derivative and divide by 1 factorial. And to find what we're calling the 0th term, the 0 indexed term, I took no derivatives and I divided by 0 factorial. So 0 derivatives and 0 factorial. And so following this pattern, if I want to find the nth term, the nth coefficient, I can simply take the nth derivative, and this notation where we use little parentheses around n, the parentheses are meant to indicate that this is a derivative. If I didn't have the parentheses here, you would assume that we were raising it to the nth power. But these parentheses, by convention, indicate that we're dealing with a derivative. So I take the nth derivative of f, evaluated at a, and then I divide that by n factorial. This is our generic formula for the nth term. So, to be totally clear, this gives us our form of our convergent power series. I'm going to write this out as a theorem so that we can circle it and highlight it and recognize how important this is. Let me box this one because that's important. But let me write this theorem out. So this theorem has to do with the form of a convergent power series that represents a function of interest. Okay, if our function f has a power series representation, and we haven't said anything about guaranteeing that a function has a power series representation, and it turns out that not all functions will. Basically, the function has to be sufficiently smooth in order to have a power series representation. But most of the functions that we're accustomed to dealing with satisfy this, things like trigonometric functions, sines and cosines, exponentials, logarithms, etc. Most of the functions that we're used to dealing with have the properties required to give it a power series representation. Okay, so if f has a power series representation, and another word you may hear is a power series expansion, representation, also known as a power series expansion. So just so you know, if you hear that term, that's probably what they're referring to. At the point x equals a, such that, or so that, the following is true, are f of x is equal to the sum from n equals 0 to infinity of c sub n times x minus a to the nth on some, so this converging over at least some interval, then those c sub n coefficients are the following. C sub n equals the nth derivative of f evaluated at a divided by n factorial. So this is the whole thing written out to be totally clear. Basically what we're suggesting is we can plug this in right here for our c sub n and have the generic form of our power series representation. This is what we're ultimately going to call our Taylor series. So let's just go and make that explicit. If we plug these back in to the formula that we're looking at, so if we plug these coefficients in, we get that f of x is equal to the sum from n equals 0 to infinity of f n of a, so the nth derivative of f evaluated at a over n factorial times x minus a to the nth. And if we look at the terms that this spits out, what it's going to give us is when we plug in n equals 0, I'm taking no derivatives of f, so it's just going to be f of a. 0 factorial we said we were defining to be 1, and x minus a to the 0th power is just a 1 as well. So the first term when we plug in n equals 0, we simply get f of a. When we plug in n equals 1, the next term, I will have to take the first derivative of f evaluated at a over 1 factorial and multiply that by x minus a to the first power. So our next term is going to be plus f prime of a over 1 factorial. If we want to write that, you don't even have to if you don't want to, because it's still just 1, times x minus a. And the next term after that, when we plug in n equals 2, will be f double prime of a, the second derivative, over 2 factorial times x minus a squared. And the third term will be f triple prime of a, the third derivative, over 3 factorial times x minus a cubed, and so on and so forth, plus dot dot dot. So this is our pattern. Turns out this is the Taylor series for f of x. So Taylor series for f of x centered at x equals a. As a quick side note here, we titled this section Taylor and Maclaurin Series. It turns out that if a is 0, so if you're centering this thing at the origin, we call it a Maclaurin series, but most people still just refer to that as a Taylor series. Taylor series more generic. Maclaurin series is specifically a Taylor series centered at 0. So if a equals 0, it is or can be called a Maclaurin series. Basically, the two guys kind of developed this separately, and Taylor was the lucky one to get it generically named after him, and that's the name that we all recognize. And Maclaurin, unfortunately, focused mostly on one centered at the origin, and so he only kind of got his name tagged on as this special case. So we have an approach that will work to find Taylor series or Maclaurin series for a bunch of different functions. And before I do a bunch of examples, because we're going to do some examples, I want to find a Taylor series for, say, an exponential function, and find one for sine and cosine that we've kind of already seen. So we can look at a whole bunch of them. I want to think about what is required. If we come back up to our theorem, we said that if f has a power series representation, then this is what it'll wind up looking like. When is that going to happen? Well, what you can see is clearly these coefficients require us to take nth derivatives. And what it basically tells us is we need the function that we're trying to approximate to be sufficiently smooth so that it has a bunch of derivatives. Technically speaking, you could try to do a Taylor series of a polynomial. And what you should get is, if this all works, you should just get back that polynomial. If I'm trying to come up with a Taylor series expansion of the function y equals x squared, when I plug in x squared for my f of x, I should eventually get this whole thing to spit out x squared when it's all said and done, because that one, turns out, doesn't need an infinite number of terms, right? What we're thinking of is this thing is essentially an infinite polynomial. If you try to approximate a finite polynomial with one of these, eventually you're going to run out of derivatives. All the subsequent derivatives will be 0, right? If I take x squared and you take the first derivative, you get 2x. If you take the second derivative, you're down to 2. By the time you get to the third derivative is 0, and the fourth derivative is 0, and the fifth derivative is 0, and all subsequent terms will basically disappear. So we can see what that happens, or you can try it on your own. Try finding the Taylor series of a polynomial, and what you'll see is you just get back that polynomial. So we can take a look at that maybe later. But for now, let's do it for functions that this is actually helpful on. So let's find the Maclaurin series, in this case, just because I want it centered at 0, of e to the x. So let's find the Maclaurin series of f of x equals e to the x. And with it, let's also find the radius of convergence, because it's not useful to find a series representation and then find out the radius of convergence is 0 and that it doesn't actually approximate the function that you were interested in, except for at that one single point. Okay, so to find the Maclaurin series, I'm just going to come back and basically do this. I want all of these terms. I want to find C0, C1, and so on. So if we're trying to find C0, the first term, remember our C0 term is basically just f of a. So in this case, it's simply f of 0. In fact, let me not even do this with a colon here. It's literally equal to f of 0. So let me just write an equal sign here. C0 is f of 0 in this case. So what is f? E to the x. So in e to the f of 0 is e to the 0, which is 1. Our first term is simply 1. What is C1? Well, C1 is going to be equal to f prime of 0 divided by 1 factorial. And what is the derivative, if you will, of our original function f of x? So what is f prime? Well, if the original function is e to the x, and the derivative of e to the x is e to the x, then f prime is also e to the x. So this is going to be just e to the x, let's write it more clearly, e to the x over 1 factorial, and we're evaluating it at x equals 1, just to be clear. Sorry, at x equals 0, to be clear. And that's going to give me a 1 up on the numerator, right? E to the 0th is just 1, and we also have a 1 in the denominator, and so this coefficient turns out to also be a 1. And if we try to find C2, C2 is going to be f double prime of 0 over 2 factorial, according to our rule of coefficients here. So I'm just finding this, we found this, now we're finding this right here. We haven't started factoring in our x minus a's yet. We'll come back to that once we have all the coefficients. So this coefficient, what is the second derivative of e to the x? Well, that is also e to the x. And we're now dividing that by 2 factorial and evaluating the whole thing at x equals 0. And so I'll get a 1 in the numerator, and I will get a 2 in the denominator. It's just 1/2, or we can keep it if we want as 2 factorial. Let's find C3. It's going to be f triple prime of 0 over 3 factorial, which again is the third derivative is still going to be e to the x. We're just dividing by 3 factorial. We're evaluating the whole thing at x equals 0. We're still going to get 1 in the numerator, but now we have 3 factorial in the denominator. And in general, what is the nth term? Well, it's going to be the nth derivative of f evaluated at 0 over n factorial, which for us is the nth derivative of e to the x is still going to be e to the x. But now we're dividing by n factorial and evaluating it at x equals 0. And we're still going to get 1 in the numerator, and we're just going to get n factorial in the denominator. So if we plug these in, we get a series representation that looks like the following. Our e to the x, which is our original function, f, looks like, zoom out so we can try to see this all on the screen at once. Here's the pattern that we're trying to, let me see if I can get both on the screen. There we go. So here's the generic formulation of it. Here's all the individual terms. Let's write them both out. The first one is just f of a. That was this 1 that we found. That's our C0. Plus, here's C1 times x minus a. So C1 was 1. X minus a, what is our a? A is 0 in this case. We're finding it centered at 0. I should have made that totally clear. Find the Maclaurin series. Oh, I did make it totally clear. I called it a Maclaurin series. So we're evaluating it at 0. So my next coefficient is 1 times x minus 0, which is just x. And then I have C2 times x minus a squared. C2 is 1 over 2 factorial times x minus 0 squared plus 1 over 3 factorial times x minus 0 cubed. And I don't need to bother writing all those x minus whatevers. So if we clean it up, it really just looks like 1 plus x plus, if you want to write the coefficients out, we could just write it as x squared over 2 plus 3 factorial is 6. So the next one would be x cubed over 6 plus dot, dot, dot. And generically, it's the sum. If we write our whole big formula out, our closed form representation of this, it's the sum from n equals 0 to infinity of basically x to the 0, or sorry, x to the n over n factorial. Okay, so this is our representation of e to the x. This is what the first few terms look like if you actually write out the numbers. But the pattern is it's always n factorial in the denominator. Now let's try to find the radius of convergence. So let's find r. Let me zoom in just a little bit. How can we find r? Well, the way that we did it before was typically with either like the ratio test or the root test. And in this case, because we're dealing with factorials, the ratio test is going to be the easy way to go. So I want to find r using the ratio test. And so the ratio test says, again, just to remind you, we want to take the limit as n goes to infinity of the absolute value of an plus 1 over an, and see if this gives us some number L that is less than 1. So basically, when do we get this to be less than 1? Whenever it's less than 1, then it converges. And we will just test to try to find basically what values of x allow for this ratio to be less than 1. And if it turns out that it's only one value of x, then the radius is 0. If it turns out it's every single possible value of x, then it has an infinite radius and it converges everywhere. So we'll take a look at that. So what is our a sub n? Our a sub n is right here. This is what we're calling our a sub n, our nth term of our series. So there's our a sub n. So what does it look like in our specific case? We have the limit as n goes to infinity of this thing evaluated with n plus 1. So x to the n plus 1 over n plus 1 factorial. And then I'm just going to skip ahead, and instead of dividing by the other fraction, I'm just going to multiply by the reciprocal. So that'll be times n factorial over x to the n. So I've skipped a step here where normally we would write this over the reciprocal of this. Instead, I'm just skipping that step. Instead of doing a fraction divided by another fraction, I'm doing a fraction times the reciprocal of the other fraction. And we cancel whatever we can in this case. I have n plus 1 factors of x on top. I have n factors of x on the bottom. All but one of them will cancel. And so I will wind up with the limit as n goes to infinity of, we'll wind up with one factor of x surviving on the top. And on the bottom, we wind up with an n plus 1 surviving, because n plus 1 factorial is basically n plus 1 times n factorial, and the n factorials will cancel. And let me not forget my absolute values, but this is what I'm taking the limit of, and regardless of the value of x, right, we can pull the x out if we'd like. We could write this as absolute value of x times the limit of, as n goes to infinity, of 1 over n plus 1. And I don't need absolute values here because, again, n is always non-zero. It's either 0 or positive. Or sorry, it's always non-negative. It's either 0 or positive. What does this limit go to? Well, as n gets very large, this whole thing, regardless of the value of x, is going to 0. So it always converges. It is always going to give us 0, which is less than 1, regardless of the value of x. What does that tell us? That means that the radius of convergence is infinite. It converges for every single possible value of x. There are no restrictions on what x can be. Pick any finite value of x you can come up with, and this thing's going to go to 0, and it doesn't matter what the x value is. So, therefore, our radius of convergence is infinite. And again, I'm going to just cheat and write r equals infinity, which is technically probably not something you should write. You can't have something be equal to infinity, but that's the idea. In words, it has an infinite radius of convergence. Another way of saying that is it converges for all x, etc. So that's good news. Basically, we found a Taylor series, or in this case, a Maclaurin series representation of e to the x, and it turns out it's valid for all values of x. This thing works everywhere. It does rely on this plus dot dot dot. We need to have an infinite number of terms for this equality to be exact. But the idea is that you can also approximate e to the x, even if you truncate the plus dot dot dot. These terms, as you can see, are going to get smaller and smaller and smaller. And eventually they won't count that much, and they'll only be affecting our approximation of e to the x maybe in the 7th or 8th decimal place or something. And if you're good with only having 5 decimal places of accuracy, then you're good at that point, and you can just truncate your infinite series, cut it off there. Okay, so this is our Taylor series representation for e to the x. Let's look at a couple of other ones. And let's talk about what I just said here, actually, before we look at a couple of other ones, because there's going to be a bunch. But let's talk about one other thing. This is kind of an important question we should ask ourselves, probably before I move on and do a bunch of other examples. When is a function equal to its Taylor series? When do they represent the same thing? So when is a function equal to its Taylor series? We've kind of already talked about it, but let's say that we're going to let t sub n of x be what we're going to call a Taylor series that isn't a full series. It doesn't go to infinity. This is our truncated Taylor series. So it's instead going to be the sum from, I'm going to change because I'm using n down here. Let me use a counter of I. So let's start at I equals, say, 0 to n of the ith derivative of f evaluated at a over I factorial x minus a to the ith power. So this looks exactly like what we did for a Taylor series, but instead of using n as our counter and going up to infinity, I'm starting with, I'm using I as our counter, and I'm only going up to some finite value n. And this is kind of the way that the book will define this. This is what we're going to call the nth partial sum of our Taylor series. So it's going to be the nth partial sum of the Taylor series. Oftentimes what we'll refer to this as is the nth degree Taylor polynomial. And in practice, these Taylor polynomials are usually what get used, right? We're just going to use an approximation. There's no way you can actually compute the infinite series every single term. So we'll just truncate it at some point. In this case, it's the nth degree Taylor polynomial because we're going up to the highest value of I that'll show up will be n, meaning the nth power is going to be the highest factor essentially of x, or the highest multiple of x. We'll have an x to the nth power, making it an nth degree Taylor polynomial. So for the one that we just did, where f of x was equal to e to the x, we would say that our t1, the first degree Taylor polynomial, would just include the terms the 1 plus the x, right? It would just be up to the linear terms here, right? 0th term, first, second, third, and so on. So 1 plus x, that's our first degree Taylor polynomial. If I wanted the third degree Taylor polynomial, it would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial. We would go up to the cubic term so that it would be a third degree Taylor polynomial. So similar to what we did back when we talked about the remainders and trying to approximate the remainders of a partial summed series. So if we're trying to figure out the sum of a series, we have a partial sum, how much is left before it converges to the exact value. We'll have the following. So similar to what we discussed back in, I don't know, this is way back in like section 11.3 or something like that. I don't even remember. But we have a similar argument and similar terminologies. So similar to before, our function f of x is going to be equal to some, basically, Tn of x plus the remainder, which we're going to call Rn of x. So if you think about the one that we just did, we would say that our e to the x is exactly equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus dot dot dot. And we can break it up into two parts. We could call this first part here our T3, our third degree Taylor polynomial, plus whatever's left over, including the dot dot dot, which goes off to infinity. That is our remainder, R3 of x. So it's the remainder that's left over after you sum up the third degree polynomial, the third degree Taylor polynomial, or the third partial sum of our original function. So again, in general, we can split the whole thing into these two parts right here. We can split up our original function into the nth partial sum plus whatever's left over. And now we can talk about this remainder and what is the behavior. So basically, if we can show that that remainder eventually is going to go to 0 as n goes to infinity, that basically if you start to include more and more terms, that the amount that's left over, that remainder, goes to 0, then the series has to converge. So that is sort of a logical way to think about it. If we can show that our r sub n of x goes to 0 as n goes to infinity, the remainder goes to 0 as n goes to infinity, then the series must converge. So, and if we do that, we can actually kind of look at the math behind that a little bit here. So essentially, if I take the limit as n goes to infinity of the t sub n of x, the nth partial sum, I can think of that as being the same thing, looking at what we've got right here. If I solve for this piece, I could just subtract the r sub n term from both sides. This is the same as looking at the limit as n goes to infinity of our f of x minus Rn of x. So what it's basically saying is this term, which represents the nth partial sum, is the same as the difference between the actual exact representation of the function and whatever our remainder is of our partial sum. So basically, if this thing's going to 0, then we're going to eventually get these two things to be representing the same thing. And that's what we're about to show. So I can pull the, because there's no n dependence on f of x, I can just write the limit as n goes to infinity of f of x. That's still just f of x minus, the limit really only applies to the second term here, so the limit as n goes to infinity of Rn of x. But if we're just saying that that goes to 0, as we said right here, if the limit of Rnx goes to 0 as n goes to infinity, so this limit is 0, then this whole thing is just equal to f of x. It's another way to think about it mathematically. So what we've suggested is basically, in this case, the limit as n goes to infinity of the nth partial sum, our Taylor series, will be exactly equal to the original function that we're interested in. We can write a theorem related to this idea, and so that's what I'll do now. There's a lot to unpack in this section, so let's look at this theorem. It says if f of x is equal to Tn of x plus Rn of x, so the nth partial sum plus whatever remainder there is, where these are defined as we defined them earlier, so where Tn of x is the nth degree Taylor polynomial, and the r sub n, that limit goes to 0, so, and the limit of that remainder, r sub n of x, if that is equal to 0, at least over the interval that we care about, so for all the values of x centered at a within a radius of capital R, and just keep in mind, this r sub n and this capital R are different things. This r sub n is a remainder. This capital R is the radius. They're different r's. Then f of x is equal to the sum of its Taylor series, the full sum. Taylor series on that same interval. So all of this is basically a really long, complicated way of coming to a theorem, a definition that's really kind of intuitive. It's just saying that basically the function and its Taylor series representation are going to be exactly equal, basically whenever you can get the series to actually converge, when this remainder goes to 0 on whatever interval we care about. Okay, so that's all we're saying. Is basically we're saying that when the Taylor series converges, it's going to converge to the actual function. Okay, so let's look at, I said a minute ago that we were going to look at some more examples. Let's look at one now that's going to be a really useful one. It's something that you probably have seen in some form or another in a previous class. It's called the Binomial Series. And it's going to be the next one that we're interested in. So the Binomial Series. Okay, so a binomial is basically just a something with two terms. It looks like this, and we could raise it to some power. A plus b to the n, that's a binomial. It's called a binomial because there's two different terms that show up here. So that's kind of going to be what we're looking at. Let me erase this one because this isn't quite the notation we're going to use. But let me define this. If k is some real number, and we also have some x such that the absolute value of x is less than 1, then it turns out we can represent a binomial series as follows. 1 plus x to the k. And notice that this just says k is a real number. It doesn't even require k to be an integer. You can have irrational powers here. We could raise this to the pith power if we wanted to. It looks like the following. It looks like the sum from n equals 0 to infinity of, let me just write this notation down. We say we would read this as k choose n. This is, if you've ever seen a class where you talked about binomial coefficients, this may have shown up in a stats class you took or something like that. There's a formula for this that we can look at in just a minute, but basically let me just get the whole thing down. So k choose n times x to the nth. And what it looks like is a 1 plus kx plus k times k minus 1 over 2 factorial times x squared plus k times k minus 1 times k minus 2 over 3 factorial times x cubed plus dot dot dot. So let me do a side note here on what this term looks like. It's basically going to give us what we call the binomial coefficients. So k choose n, or we just write them in parentheses one above the other, is basically a function that involves a bunch of factorials. It looks like k times k minus 1 times k minus 2 times dot 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 all the way up to k minus n minus 1. So, sorry, k minus n plus 1 over n factorial. And these are called the binomial coefficients. And there's different ways to see where these binomial coefficients come from. One place you may have seen them is it turns out the binomial coefficients are actually related to like Pascal's triangle. So you would see like the coefficients with the right combination. If basically we let k be equal 3 here, and we let n be various numbers 0, 1, 2, and 3, you would get the coefficients 1, 3, 3, 1. If we let k be 4, you would get the 1, 4, 6, 4, 1. If we let k be equal to 5, you'd get the 1, 5, 10, 10, 5, 1 coefficients. So Pascal's triangle being the thing that looks like this: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, where you generate each term going down the triangle by summing basically the two terms above it, and you always just put ones along the edge here. So these numbers in here are the binomial coefficients for various values of k, and you would pick a different value of n to generate each one of these numbers. Another place that it shows up, incidentally, is in statistics. It shows up a lot in probability. In particular, there's something called a binomial probability distribution, and it has to do with how many combinations you can choose. So if you let k be the number of objects you have, and you're selecting n of them. So imagine I've got like 3 marbles, and I want to know how many different ways are there that I can pick out 2 of the 3 marbles. So if I have 3 marbles, one is red. Let's write this out. If I have 1 red, 1 blue, and 1 yellow, here's my set of marbles. So this would be k equals 3. How many ways are there that we could choose 2 of them? So if I wanted n to be equal to 2, the idea is, how many groups of 2 could I come up with? Well, I could have red, blue, I could have red, yellow, or I could have blue, yellow. And I can come up with, it turns out, these are meant to be curly brackets, I could come up with 3 total combinations. And again, we don't care about the order. Red, blue, and blue, red is the same thing as far as we're concerned. So we have 3 combinations. And that's the idea. If I plugged in these 2 values into this formula, it should spit out the number of combinations. So let's just verify that that's the case and that I didn't screw up my explanation here. Oops. So let's just see what 3 choose 2 would look like. So again, 3 is our value of k, 2 is our value of n. And so we'd plug into this formula, and I would get, on top, we get k times k minus 1 all the way down, so it would be 3 times 2 times all the way down to k minus n plus 1. But what is this? If this is 3 and this is 2 plus 1, so I have 3 minus 2 plus 1. So 3 minus 2 is 1, plus 1 gives me to 2, so I actually just stop once I get to 2. 3 times 2. So there's really only going to be 2 terms in this one on top, 3 times 2. And then we divide by 2 factorial, which is also just 2. And so we get 3 times 2 on top, 2 on the bottom, they cancel, and we just get 3 as the result, which is exactly what this thing said here. We've got 3 combos. So that's how this thing looks, and this is one of the things that one of the contexts where this shows up. I'm going to erase this, but just so you know, you may have seen this before. It's not impossible that you've taken a class where you've talked about either Pascal's triangle or, say, in a statistics class, and you talked about combination functions, or a combinatorics class where this type of thing showed up. Let's see if I can actually erase it here. There we go. Okay, so this is what we're dealing with. Let me just get that piece deleted as well. Okay, so this is what that function does. It basically just generates numbers. The output of this is you plug in a value of k, you plug in a value of n, and it's going to spit out a number for us. And that number is going to be the coefficient that we're interested in here. So let's do an example where we can kind of see this in action. So let's say I want to find the Maclaurin series again, so we want to center it at 0 for f of x equals 1 over the square root of 1 minus x squared. So what you can think of this as being is basically 1 minus x squared raised to the negative 1/2 power. And now I have something that looks a lot like what we've got here. It's just I've replaced x, what we had here is x, I've replaced it with a negative x squared, and the value of k is negative 1/2. This formula here is a little bit wonky. This is the formula that works for integers. If you use non-integer values, like the ones that we've got here, then this kind of starts to get a little bit wonkier because we can't really define these things quite as clearly here. You can't just define it in terms of factorials, but this formula will still work. All that it requires is that k be a real number, and it will work in this formula. There's a simpler form for this formula if you restrict it to integers that just involves factorials, but in this case, this formula will work even for values of k that are not integers. Okay, so long story short, let's do what we're talking about here. So what I'm suggesting is that this thing that we're looking at, 1 minus x squared raised to the negative 1/2 power, is going to be equal to the sum from n equals 0 to infinity of negative 1/2, that's my value of k, choose n, times negative x squared, because that's what we're plugging in place of our x, right? So if I swap in x over here with negative x squared, I just do the same thing over here. That's one of our substitution properties that we looked at, raised to the nth power. And so if we start to generate individual terms, what does the first term look like when we plug in n equals 0? So we'll come up to this formula, and basically the first term is going to look like, in fact, let me do it underneath. We'll write the value. So I'm going to leave a place for us to put the value in, but this value is going to be generated by doing negative 1/2, 0, and that's going to be the coefficient, and we're going to multiply that by negative x squared to the, in this case, 0th power. So this whole piece will just become a 1. So something times a 1. So what is this term going to look like? Well, all we need to do is plug into the formula here. What happens when I plug in negative 1/2 for k, and I'm supposed to write it times, so basically then subtract 1 from that, do that as many times, all the way till we get down to k minus n plus 1. So I just need to know where we're going to stop. K minus n is going to be negative 1/2 minus 0 plus 1. So negative 1/2 minus 0 is still negative 1/2, plus 1 is positive 1/2. So I need to somehow start at negative 1/2 and decrease all the way till I get to this positive 1/2. Turns out that's a really weird thing to think about, and as a rule, whenever you choose 0 for your bottom number here, turns out this is by definition always going to be a 1. Another way to think about it is, because when I talked about it as the combination function, You can think of it as kind of how many ways are there to create combinations of size 0. So if we go back to my marble example, if we had a red, blue, and yellow marble, and that's our set, how many ways are there to pick 0 of these out? Well, there's always only one way to pick 0 from a set, and that is going to be the empty set. I just don't pick any of them. So by definition, anytime you have k choose 0, by definition, is always going to be equal to 1. So that's one thing to keep in mind. Regardless of the value of k, if you're choosing 0 of them, you're going to get 1 out of this. That's probably the easiest explanation. Otherwise, if you try to actually plug in the -1/2 into this formula and 0 for our n, things start to look really, really weird. And you don't actually know where to start and end this thing, because you're supposed to be starting at -1/2 and decreasing until you get to +1/2, which doesn't make any sense. So just keep that in mind. There are a few of these weird cases, but the easiest explanation is anytime you are having 0 for your value of n here, you're always going to get 1. So by definition, that term looks like 1. So let me erase these and delete that. And let's look at the next term. The next term will hopefully start to make a little bit more sense. So that was our first term. Now I need to go to the case where n is equal to 1. We've done n equals 0. Now let's go to n equals 1. When n is equal to 1, again, we're going to get something times, in this case, that coefficient will be multiplied by -x squared to the first power. So we're going to eventually get this times -x squared. And we just need to figure out this coefficient. This coefficient right here is going to be -1/2 choose 1. So I want to figure out what this looks like by plugging it into our weird formula up here. So when I plug in, we're going to always be starting at the value of k. So we're going to start at -1/2, and we're going to decrease until we get to a value, in this case, of, we need to figure out what this last term is. So -1/2 minus n plus 1. So -1/2 minus 1 plus 1. -1/2 minus 1 plus 1 is just going to be -1/2. So I need to go from -1/2 all the way down to -1/2. The idea is that in this case, it's only going to have one term. Even though it looks like there's a lot of terms here, basically when we have n equals 1, we're only going to have this first term show up. And so it's just going to be -1/2 over 1 factorial. -1/2 over 1 factorial, which is just going to be equal to a -1/2. And so we'll look at that in a minute. Plus, the next term after that is again going to be some coefficient times, we're now plugging in n equals 2. What do I get over here when n is equal to 2? So -x squared, the whole thing squared. So -x squared squared is what we're going to get, which will wind up just being a positive x to the 4th. And now I need this coefficient. And this coefficient is going to be, again, -1/2. Now choose 2. And see how this works. How does this formula work in this weird case? So I'll plug that in over here. We're going to start at -1/2, and we're going to decrease until we get to -1/2 minus 2 plus 1. So what value do we get here? -1/2 minus 2 plus 1. That's really just the minus 2 and the plus 1 canceled to give me just a -1. And so it's -1/2 minus 1. I need to go down from -1/2 to -3/2, multiplying together. So I'm going to get a -1/2 times a -3/2. And that's when I'll stop. And then I divide by n factorial. So in this case, 2 factorial on the bottom. Plus ... This is getting tedious, so we'll just end it there. So this is how we would do this. We would clean it up a little bit after the fact. So 1 times 1 is just 1. Over here, this negative sign will cancel with this negative sign, and I'll just have 1/2 x squared. And then for this term over here, these two negative signs will cancel. I'm going to get a 3/4, but I'm dividing that by 2 factorial, so it's really going to be 3/4 over 2, which is going to be 3/8. And the result of this term when I square it is negative x squared squared is going to be just x to the fourth plus dot dot dot. So that's what the first three terms at least of this particular, the series representation of this thing would look like. So that's how you can do one of these problems. And it's, again, it's a little bit ugly, but that's kind of the idea here. So, let's try one maybe that doesn't have to do with the binomial series. We'll look at some other ones that are a little bit more simple, but this is the one that we kind of need to have memorized. If you want 1 plus x to whatever value of k we have here. So we could do square root functions because of this. We just did one that was a 1 over a square root function. Basically, this is going to give us a way, this general formula here is going to give us a way of representing rational functions and radical functions in particular, actually. I should have said radical functions. So 1 plus x to the square root, the 1/3 power, whatever, it's going to give us a way to represent those as series. So just keep that in mind. We can do another one of those. We'll do another one of those examples before it's all said and done. But let's do one that doesn't require the binomial expansion, just so that we can maybe not do a bunch of nitty-gritty algebra with this horrible, horrible formula right here. Okay, so let's do a different one instead. Let's say I want to do, let's find the Maclaurin series for an f of x that looks like x cosine of x. So basically, we are trying to find our sum from n equals 0 to infinity of a bunch of cn's x to the n's that look like this. What I'm going to do is utilize, so that I don't have to treat this whole thing as the function and start taking derivatives, which we could do. So our Taylor series formula says that we basically just look at f evaluated in this case because it's a Maclaurin series. I'd look at f of 0. Then we'll also need f prime of 0, f double prime of 0, and so on. So that involves taking derivatives of this. Those derivatives are going to get increasingly complicated because it's a product of two separate functions of x. It's x times cosine of x. But I can cheat. We can separate out this x and use the properties of series that we were talking about earlier. I can basically factor this x out, just simply find the Taylor series representation of cosine x by itself, and then multiply every single one of those terms by this x. So what I'm suggesting is we could either treat finding a Taylor series of this whole f of x, or instead, what we're going to do is find basically the Maclaurin series. Okay, so let me just write this out. We could have found this for the f of x equals x cosine of x, but instead what we're going to do is find the Maclaurin series for simply some new h of x, I'll call it, which is just going to be cosine of x, and then multiply that by x. And that's going to be a lot easier because this is much easier to take derivatives of than this, especially repeated derivatives, second, third, fourth derivatives of this thing right here. So we've broken this up into two parts, and this is a very good tool in general. If you just are multiplying by x or an x squared or something like that, something that is a polynomial term, then just find the Maclaurin series for the non-polynomial part and then multiply every term by that piece that you're missing, whatever that factor of x is. So what I want to do is instead find the Taylor series, or the Maclaurin series rather, for simply cosine of x. And to do that, I know that cosine of x is going to be equal to, we just need to remember it's going to be h of 0 plus h prime of 0 over 1 factorial times x minus 0 plus h double prime of 0 over 2 factorial times x minus 0 squared, plus, and so on and so forth. I can write another term here maybe. H triple prime of 0 over 3 factorial times x minus 0 cubed. And let's even do one more for good measure. So after basically the third derivative, that's when I start using just parentheses. I can see 3 little dashes to do the third derivative, but I don't want to keep track after that. So I'm going to write that as h parentheses 4 to indicate the fourth derivative over 4 factorial times x minus 0 to the fourth plus dot dot dot. So this is what we're doing. This is basically, we've defined h of x to be cosine of x. That means that we can define our Maclaurin series as follows. So I just need to know what basically h of x is. What is h prime of x? What is h double prime of x? What is h triple prime of x? And in this case, we're going to go all the way up to fourth derivative at least. Maybe more after that, but luckily there's some nice patterns. So what's the derivative of cosine? The derivative of cosine is negative sine. And what's the derivative of negative sine? That's going to be negative cosine. What's the derivative of negative cosine? That is sine. And what's the derivative of sine? We're back to cosine. And this could continue on indefinitely. And now we're just going to evaluate these basically each at 0. So we get zoom out so we can get it all on the screen at once, at least the relevant pieces. We're going to get that our cosine of x, approximation, our Taylor series for it, is h of 0, so that's the first term. So here's h of x. When we plug in x equals 0, I just have cosine of 0. What's the cosine of 0? It is 1. Plus h prime of 0 over 1 factorial. Here's h prime. It's negative sine of x. So I need to plug in 0 here. What is h prime of 0? It's negative sine of 0. The sine of 0 is 0. And so this term is technically negative 0, but it doesn't matter. 0 over that 1 factorial times x. I'm going to stop writing all the minus zeros that we've got here. Just write them as the x's. So that term is, this whole term is gone. It's 0. Plus, now I need this term. I need h double prime of 0. So here's h double prime, and I'm evaluating it at 0. So I need negative cosine of 0. Cosine of 0 we just said was 1. This negative sign will make it negative 1. So this term is going to be negative 1 over 2 factorial times x squared. And that's the x squared that I'm getting right here. This gave me a negative 1. The next term will be the third derivative. The third derivative is down here. It's another sine function. Whenever we evaluate sine at 0, you get 0. So this is going to be another term that just goes to 0. Plus, skipping on to the fourth derivative term here, which I will move over so we can see it. The fourth derivative term we have here is back to cosine. I'm evaluating cosine at 0. So when we evaluate cosine at 0, I just get 1 again. So this numerator up here is going to be 1 over 4 factorial times x to the fourth plus dot dot dot. And if we clean this up, we get something that hopefully looks familiar because we've done this a couple of times now. It's going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. And hopefully you sense the pattern. The next term would be minus x to the sixth over 6 factorial plus x to the 8th over 8 factorial minus dot dot dot. So the sign alternates back and forth, plus or minus, plus or minus. And we only wind up with the even terms because all of the odd derivatives wind up giving us sine functions. And when we evaluate sine at 0, it's always going to be 0, killing all of the odd terms off. So this is what cosine looks like. We have a closed form representation of this that we've seen before, but to make it totally clear, here's what it looks like. It alternates signs, so it's going to have -1 raised to the, let's say, the nth power, but that'll make sense because we're starting at n equals 0, so -1 to the 0th power is still going to be 1. And that would give me this term. And then you can see that the powers, if you think of this as, again, being n equals 0, n equals 1, 2, 3, 4, and so on, you can always see that the power of x is double whatever n is. So we're going to have x to the 2n, and then we're going to divide by that exact same number, factorial, so 2n factorial. So this is our representation of cosine. This is going to be an important one to know. I'll point you to a table in the book, and maybe I'll even try to download that table and just give you a table of common important ones that are good to just kind of know and recognize. Maybe 5 or 6 Taylor series that are worth kind of knowing. But how do we now modify this? Remember, the original problem was we were looking for x cosine x. Here I've given you the Taylor series, or in this case the Maclaurin series, for cosine of x. How do we modify it to get x cosine of x? So to get a series representation of x cosine of x, all we need to do is multiply our current series by x. So x cosine of x, instead of looking like the one that we just wrote right here, I just multiply every term by x. So that first term isn't going to be 1, it's going to be x. The next term isn't going to be an x squared, it's going to be an x cubed over 2 factorial. The next term isn't going to be x to the 4th, it's going to be x to the 5th over 4 factorial, minus x to the 7th over 6 factorial, plus x to the 9th over 8 factorial, minus ... And similarly, we can come up with our sort of closed form expression for the nth term and write this as the sum from n equals 0 to infinity of the -1 to the n, that hasn't changed, dividing by 2n factorial, that hasn't changed. The only thing that changed was this. It's not x to the 2n anymore. It's now x to the 2n times another x. X to the 2n times another x. And how does that modify that term? Well, now that term is going to look like x to the 2n plus 1 power over, again, 2n factorial. And so here is our Maclaurin series representation of x cosine x. This turns out to be another one that I'll just mention. The Taylor series for cosine converges everywhere. It doesn't have a limit on the convergence. But let's look at maybe like one last example of this, because this video is getting long. I promise we'll do some more examples in review for the exam 3 and everything. Let's just do one more for this video because it's dragging on at this point. Let's do one that's not centered at 0. Let me do this one. Let's find, so in this case it is a true Taylor series because it's not necessarily centered at 0. But find the Taylor series for, let's say, f of x equals 1 over x squared. And let's have it centered at x equals -1. Okay, so in this case, the f of x that we're interested in is our 1 over x squared, or you can think of it as x to the -2 maybe, would be an easier way to write it. And then that means our f prime of x, the derivative of this will be negative 2x to the negative 3. The second derivative is going to be, we'll have that negative 2 down there. We'll multiply it by a negative 3, so it'll be negative 2 times negative 3 x to the negative 4. The third derivative will be a negative 2 times a negative 3 times a negative 4 x to the negative 5th. And let's go up to the fourth derivative again just to have enough. So here's our fourth derivative. It'll be all those same constants times a negative 5x to the negative 6th. And now we're going to need to evaluate these all centered at basically the new point. So I want to know what each one of these is evaluated at x equals negative 1, evaluated at x equals negative 1, and so on. Okay, so when I plug in this first one, when I plug in negative 1 for x, and we're raising it to the negative 2 power, you can think of this as basically just 1 over negative 1 squared. That whole thing is just 1. So that first coefficient is just going to be 1. When we plug in the next value here, it is the same as negative 2, and you can think of it as over negative 1 cubed. Negative 1 cubed is going to be negative 1. The negative 1 down here will cancel with the negative of the 2 up here, and will be positive, and we'll just wind up with a positive 2. If we do the next one here, so multiplying those two numbers together, I've got negative 2 times negative 3. That's going to be a positive 6 that we'll have in the numerator. And I can think of the x to the negative 4th evaluated here as just being a negative 1 to the 4th in the denominator. And that's going to be positive 1, so we're just going to get a 6 out of that. For the next one, we've got negative 2 times negative 3 times negative 4. That's going to be, so 6 times negative 4 is negative 24. So we've got negative 24 in our numerator, and now we're dividing that by, in this case, negative 1 to the 5th power in the denominator. So that's also going to be negative again, and we'll wind up with just positive 24 on this thing. Doing it for the last one here, multiplying these together, these gave me negative 24 times a negative 5 is going to be positive 120. I'm dividing that by negative 1 to the 6th, which is positive again. So this is just going to be 120, and so on and so forth. So here are the coefficients that I've got when I evaluate this thing at negative 1. And we now get the following. So we get our f of x that we're trying to approximate is going to be equal to the sum from n equals 0 to infinity of the nth derivative of f evaluated at a divided by n factorial. These are the coefficients that we just already found, times x minus a to the n. So I've already found the first 5 of these terms. We found 5 of these, and I just need to multiply them out here. This is equivalent to, if we write them out term by term, the first coefficient was, we got out of this one, so it's our f of x. I didn't quite get them all because I haven't divided by the n factorials here, so let me just write that down as well. But I've got all the f values, so I've got all of the numerators basically figured out. That's what all of these numbers are. Okay, so for the first one, when n equals 0, I'm taking no derivatives. I'm looking at this one. We got a 1 on the numerator. We're dividing it by 0 factorial, which by definition is going to be 1. And we're multiplying it by x minus a negative 1 to the 0th power. Okay, so that's the first term. The next term will be plus. We now need f prime of a. So we already did f prime of a. It was 2 when we evaluated it at -1. So 2 over, in this case, 1 factorial, because we're doing n equals 1, so over 1 factorial, times x minus -1 to the first power, plus the next one is going to be 6, that's my f double prime of a, so when n is equal to 2, we have f double prime of a, that was 6 in the numerator, over, in this case, it's going to be 2 factorial, because n equals 2, times x minus a -1 squared. And if we just look at the pattern, you can kind of see what's going on here. The next one's going to be plus that 24 over 3 factorial times x minus -1 cubed. And the next one will be that 120 divided by 4 factorial times x minus -1 to the 4th power plus ... And these have a lot of nice simplification that we can do. The x minus -1 is just x plus 1. In this case, it's to the 0th power, so it doesn't matter. This whole thing here just simplifies to 1. The first whole term is just a 1. This next term is 2 over 1 factorial, so this is just 2 times x plus 1 to the first power. So this is plus 2 times x plus 1. The next term, this one, I'm going to take 6 and divide it by 2 factorial. Notice that the numerators are really, right, this is 2 factorial, this is 3 factorial, this is 4 factorial, this is 5 factorial. And what we're going to wind up with is basically 3 factorial over 2 factorial is just going to leave me with a factor of 3 here. 4 factorial over 3 factorial will just leave me with a factor of 4 here. And so I'll basically be getting a bunch of, basically the value n plus 1 for all of these. So let's do this next one. 3 factorial over 2 factorial, 6 over 2 is just 3 times x plus 1 squared. Then the next term is going to be simplifying between these two, so 24 divided by 6 is 4, as we expected, times x plus 1 cubed. 120 divided by 24, that's going to give me the 5, as expected, times x plus 1 to the 4th, plus ... So here is my polynomial so far, centered at -1, that's equivalent to this value, the function 1 over x squared that we've got here. And I can write what this looks like at the nth term as follows. So it's the sum from n equals 0 to infinity of thinking about each of these terms. So when n was equal to 0, it spit out this term. I can think of that as basically an n plus 1 being the coefficient times x plus 1 to the nth. So in this case, x plus 1 to the 0th is just 1, and I have 0 plus 1, which is also 1. So I just wind up with 1 times 1, which gives me this term. The next term, I get 2. So again, think of this as the 0th term, the first term, second, third, fourth, and so on, and it's easy to start to see the pattern. When we're at the first term, the coefficient's 2. When we're at the second term, the coefficient's 3. When we're at the third term, the coefficient's 4. That's what gave me the hint that this should be an n plus 1. The power of the x plus 1 that we're getting is the same. It matches which position at. So when we're at n equals 1, the power is 1. When we're at n equals 2, the power is 2. And that's what told me I've got an x plus 1 to the nth, is this term here. And then we just come back and just verify that this also works when n was equal to 0. And it does, because anything to the 0th power is just going to be 1 by our definition. So here is the closed form for the sums given the nth term of our series. So this is kind of the approach you can take. There's different things you can do on a lot of these, but I will point you guys to a table. In fact, I will probably try to post a PDF of that table in Blackboard and point you there for a bunch of common Taylor series. And just know that we're going to do a lot of problems that involve, and you'll see this on the homework, that involve modifying a known Taylor series in the way that we did here. So given that you know the Taylor series for cosine of x, how do you do x cosine of x? You don't need to go through all of the work here. You can use the known Taylor series. You can basically start at this jumping off point down here in order to get the final result that we got down here. So that's going to be one common thing. You will have at least one or two problems that will require you to find a Taylor series from scratch in the way that we did here, or in the way that we did here, although hopefully not with this ugly formula for the binomial coefficients, or similarly as we did way up here for e to the x. So you'll have somewhere you basically come up with the Taylor series from scratch, but a lot of them will be, how do you modify a known Taylor series to come up with a new Taylor series for a function that isn't one that you necessarily know right off the top of your head. So you'll have both types of problems. Okay, so again, we'll do some more examples before the exam rolls around, but hopefully these are enough to get you started. This is a big homework assignment, so definitely spend some time and make sure you understand and reach out with questions on this stuff.